essentially how the roots of CIMSS began, essentially was Bill coming back here to work on VAS with Franz Zuma, right, about sounding. And so Wisconsin has long been recognized as the place to do atmospheric sounding, temperature, moisture, ozone, trace gases, etc. And that heritage is still here at Wisconsin. And so I thought it would be appropriate to bring in a wonderful scientist, Elisabeth, to talk about some of the sounding activities that are going on here at CIMSS. So.
Thank you. Yeah, I would like to talk about retrievals from hyperspectral infrared radiance measurement. To draw your attention to our recent release of our UW hyperspectral retrieval package. This package has been released under CSPP, the Community Satellite Processing Package, and we wanted to provide the scientific community, so you, with the ability to obtain your own real-time retrievals, sounding profiles, cloud parameters, surface parameters from hyperspectral measurements from all of the polar orbiting sounders. So we have EAS, EASI, and CRIS, and we want to do this on single field of view resolution. So accurate soundings are very useful for a variety of applications. For example, the capability to retrieve mesoscale temperature and water vapor, temperature and moisture variation, and also stability changes that will really help, for example, NWP or weather forecast applications. So this package now, it is based on the dual regression retrieval algorithm. It's the only one, the only publicly available retrieval package to convert now hyperspectral radiance measurements, so that's level 1, to retrieval level 2 products. So in the first few slides, I would like to show you what kind of information you can extract from a hyperspectral infrared spectrum. The Planck function on the top here, B, describes the radiances emitted by a black body at a certain wavelength. When infrared radiation emitted from the surface, from the Earth and the atmosphere, passes through the atmosphere and reaches the instrument, it is modified by certain processes like absorption, scattering, emission. That's why in the radiative transfer equation over here, we are now exploring surface and cloud contributions, also contributions from the sun. The Planck function is now modified by this factor here, and that's the derivative of the transmittance, which depends now on the distribution of the absorbing gas and also on the spectroscopic features. So we have radiances like this. This is a hyperspectral resolution radiance measurement for 1 pixel. And then we can convert the radiance to brightness temperature through the Planck function. And the brightness temperature is the temperature a black body would have emitting this radiance. So what do we have in the infrared spectrum? We have 2 window regions, the short-wave one and the long-wave window region. We have very strong absorption by CO2. We have the long-wave CO2 absorption band, the short-wave CO2 absorption band, and we will see in a minute that these are important for temperature soundings. We have a very strong absorption by water vapor between 4 and 8 microns. We have strong absorption by ozone, around 10 microns, and a couple of trace gases also absorbed in this region. So now, we see now that absorption with these molecules yield to these dips in the spectrum, and the coldest temperatures are now measured in the center of the strongest absorption band. That's now CO2 here, because in that wave number region, so 680, around 680 wave numbers, the radiances from below is completely absorbed by the thick and the strong lines. And only the radiances emitted by the upper tropospheric layers reaches the instrument. And then in the stratosphere, where now the temperature increases again, this produces these humps inside the absorption bands, like over here and over here. So from the measurements at certain wave numbers, we can get now information from certain height regions. From the radiative transfer equation, we see now that the radiance contains information of the temperature throughout the atmosphere and of the mixing ratio or the distribution of the absorbing gas. And now in the reverse problem, is now again given here now in terms of pressure. It's the derivative of the transmittance. And it tells you the relative contribution from each level to the measured radiance. Or in other words, it tells you the heat region, which a certain channel senses. And this is shown here in the middle panel. You see I plotted here a couple of selected channels. They peak at certain levels. For example, if we now, and now you can already see that if I have a large number of measurements like this, whose weighting functions now cover the entire atmosphere completely, then I'm able to determine a temperature profile. For example, if you look at the channel here, that's the brightness temperature, and the, represented by the red diamond here, that's a window channels. We know that the window channels, they have the information of the surface, so it peaks around the surface, and then I can directly derive a temperature, if I'm assuming now an acidity is close to 1, from the brightness temperature spectrum, which is about 290 K. So I have a temperature level and the surface is 290 K. And then, as I mentioned before, if I'm going now into the absorption band, the radiance have information from higher levels. So the green diamond, for example, the weighting function peaks at 500 hectopascal, and then similar, I can derive a temperature at that level, and so on. So inside the absorption band and at the center, we get information from radiance from even higher levels, like this one, so we have a Druckmaß. And then I have a couple of profiles, channels, which have weighting functions, which peak in the stratosphere, like this light blue one, here in the ozone absorption band, or like the black one. So from high spectral measurements, we are able to retrieve profiles at high vertical resolution. What I wanted to add here is this inversion is usually imposed or under constraint because we want to retrieve a continuous temperature profile from a finite number of measurements. Then also the weighting functions are sometimes odd, they overlap each other, and then all the measurements also have noise. So because all of this, you cannot retrieve the temperature profile exactly. Instead, you're looking for estimates. For example, an estimate, the best estimate in a statistical sense. An option, you can do a linear regression. We saw previously in the radiative transfer equation, the transmittance is strongly dependent of the mixing ratio of and the pressure of the absorbing gas and their spectroscopic features, but it is weakly independent of temperature. So for temperature, we have the problem is almost linear. So we have now the atmospheric state, which we want to retrieve from our measurements, the Y. Then we can calculate the regression coefficients, C, according to the least squares regression solution. And in practice, what we do in a regression retrieval, we calculate the regression coefficients from a large set of representative profiles. This set also contains surface and cloud characteristics. Then we apply these coefficients to real observed radiance measurements. Then we get our retrieval. And since we are dealing with high spectral resolution, so we have a really large number of channels, it makes sense to compress the radiances by the eigenvectors first. This reduces the dimension of the problem, also the noise. So we do the same thing, but instead of Y, I'm using now A, which are the compressed radiances. But otherwise, it's exactly the same thing. But here in the retrieval step, the radiances, the real radiances have to be also compressed first. This is just a summary, but I only want to say here that if you want to retrieve also from cloud contaminated radiances, you also need seconds per field of view, and a physical retrieval would take about 10 times longer. The dual regression relies on the correct cloud top determination. That's why I'm showing you in the next couple of slides a couple of cloud top pressure retrievals. For example, this is for 18th of April this year. I have from EAS, there's brightness temperature window channel, there's cloud top pressures, retrieved cloud top pressure, and then the MODIS image, the visible image. So we see that the main clear and cloudy regions are very nicely captured. For example, the high clouds around this low pressure system over here, and we have the deep convective clouds over the tropics. We have a lot of clear skies and a couple of cumulus, low cumulus clouds over the ocean, over the Caribbean, and then the cold weather system from the north. If I'm zooming into one region now, that's over the eastern west. We have this large band of very optically thick clouds. So that's the same for EAS and MODIS correspond here. And also in this smaller piece of thin cirrus, this is nicely captured. The cirrus surrounded by clear skies over here. Now for the same case now, I would like to compare now our cloud top retrievals with observations from Calliope. Calliope is the LiDAR instrument on Calypso, so I'm going to show you a cross-section along that track here. So we have here south, we're going to north. Above, I'm showing the blue dots refer to the Calliope cloud heights, the red crosses to the EAS dual regression retrievals. On the bottom, I'm showing the optical thickness of Calliope. So we see that the overall agreement is really good, but you have to consider that that EAS has a much larger footprint than Calliope, and also they operate in different spectral ranges. Calliope is a LiDAR instrument, operates in optical wavelengths. It is able to really see really nicely the thin cirrus, where the infrared sounder usually can't see those if the optical thickness is very low, for example, over here. So the infrared sounder misses this. The optical thickness is really low. And usually when this happens, sometimes the infrared sounder sets the cloud height a little lower than the actual cloud height. Now, the next case I would like to discuss is the situation when Superstorm Sandy hit the West Coast. Here now I'm using CRISS radiances. This is CRISS brightness temperature at the window channel, CRISS retrieved cloud pressures next to a VS true color visible image. And from that figure here, from the retrievals, we see that the storm's massive circulation from the Atlantic is extending towards the Great Lakes and into Canada. And also we have lots of low cumulus cloud over the ocean, so this is very well captured by CRISS. And below I'm showing now a cross-section of relative humidity through the storm center. And what we see here in the cross-section is that the clouds act as black bodies, with the exception of thin cirrus, but all other clouds act like this. That means that the radiative information from below the cloud is passed out. Now here we're showing a couple of retrieve profiles, temperature and moisture, and their locations. This is marked here in the real image. So the first one is over here. So this is in an area where the cold and dry air from the north flows southward, over here. And then we have the warm and moist air coming from the south. Number 3 is very close to the center of deep convection, so we have increased humidity. And number 4 is now located northeast of the storm center, where the cold and dry air from the north is attracted over the warm and moisture from the south. Then we have a couple of more CRISS profiles now compared with model analysis, like NCG's profiles. So retrievals is red, the model profiles are in black. What I want to emphasize with this slide and also the previous slide is that the retrieval profiles represent really a good source of reliable information on the atmospheric state. For example, you can use this kind of information, or you can get this kind of information in geographical areas where the radius of data coverage is very poor, and also the model analysis fields are less reliable. So
an estimate of how much clear region you need in order to get a temperature moisture retrieval that would go down to the surface?
Doesn't happen very often.
Not very often, so not a,
Yeah, so we are really strict. So if we see some cloudy signal in the radiant system, we don't want to.
you don't do it all of that.